Now let me start our session by reviewing the basic production system. I think most of you must be already familiar with it. Let me just have a quick recap. In production system, we have a reservoir where our fluids will be accumulating. In order for our fluids to be extracted to the surface, you have to drill a well, and this well will be acting as a conduit for the reservoir fluid to flow from the subsurface to the surface. And at the surface, you have a wellhead, basically, which is a stack of valves, so that you will be able to control what's coming out of the well from the subsurface to the surface. And then from the wellhead, your fluid will move to the separator via a flow line. And at the separator, your fluids will be separated into gas, oil, and water. In the reservoir, we have the natural energy, which will be supporting your reservoir fluids to move from the reservoir to the wellbore and to the surface. And this natural energy are called drive mechanisms. And we have active water drive, either it's bottom or edge, and we have the gas cap drive and the solution gas drive. Other than this, we also have a mechanism, compaction and expansion, as well as the gravity drainage, and also a combination of this. In gas reservoir, when the gas reservoir is supported by a strong aquifer, or we say the active water drive, the problem is avoiding this water to break through to the wellbore. But in time, you are going to see an increase in the water rate. An increase in the water rate, and you will be noticing a decrease in the gas rate also. If you are not taking any measures and solution for these fluids that break through into the wellbore, you are going to see a decrease in the gas rate, and you will eventually see your well to produce zero gas. Now let's understand our well first. What makes our fluid flow? In order for our fluid to flow from one place to another, you are going to need a differential pressure. Only when you have a difference in pressure, your fluid will flow from one place to the other. For example, for your fluid to flow from your reservoir to your wellbore, you are going to need your reservoir pressure to be greater than your flowing bottom hole pressure. Similarly, for your fluid to move up to the surface, your flowing bottom hole pressure should be greater than your wellhead pressure. Likewise to the separator. When you are producing your liquids from the reservoir to the separator, you are going to have to overcome these pressure losses as well as the hydrostatic pressure. We have the pressure losses in your reservoir to the separator, across your reservoir, your completion, your tubing, and your triple SV, surface shock, and the flow line. If you see the pressure versus the position here, if you move from your reservoir to your separator, in each components in the production system, you are going to notice pressure losses. So basically in this production system, at a time of your life of a well, there will be two fixed pressure. One is your reservoir pressure, one will be your separator pressure. So from this fixed pressure, you will be able to analyze your system. Now let's move on to the system analysis of the production system. Here, let's assume that we have a segment here. We have this segment. In this segment, you have at the upstream, you have the pressure, which is known. And from this upstream, you have the flow rate, which will flow through the solution node, which will be across the system. In this, across this segment in the middle, you have a fluid will flow out of the node, and you have the pressure in the downstream. So we will be able to calculate the node pressure as well as the flow rate at this node. because your flow into the well, into the node as well as out of the node will be equal, as well as only one pressure will exist in this node. So as I said, you have two fixed pressure, your reservoir pressure, your separator pressure. So based on that, you will be able to calculate your node pressure. Your node pressure from upstream will be equal to the reservoir pressure minus the pressure losses at the upstream components, and at the downstream, your separator pressure plus your pressure losses at the downstream. Now, if you plot the pressure versus the flow rate, you will be noticing the curve of the inflow as well as the outflow. When these two curves intersect at this point, this indicates your anticipated node pressure as well as your anticipated flowing pressure. So this will depend on your system, from your reservoir, flowing bottom hole pressure, and tubing. Now let's see the inflow. In the production system, the performance, we have the two components. One is the inflow performance, which will be your inflow from your reservoir to the wellbore. This part is the inflow performance. And you have the other components, which will be from your bottom to your wellhead or to the surface. This part is the tubing performance curve or the vertical lift performance. So when you plot the inflow, you have the highest pressure at the reservoir, the lowest pressure will be 0, or the atmospheric pressure. One thing you will notice is that when you plot the inflow curve, above the bubble point pressure, I think you know what is bubble point pressure, the pressure at which you will see the first bubble liberating out of the gas, right? So this region will be your undersaturated reservoir region. So if you are producing at this, you are going to see a single phase flow or a liquid. So when you plot the inflow, you will the magnitude of this line, the magnitude of the slope of this line will be your productivity index. Productivity index is basically the inflow upon the differential pressure. So what this productivity indicates, let's see here. For example, if your well is flows at 1,000 barrels per day with a flowing pressure of 1,500 psi and an average pressure, reservoir pressure of 2,000 psi, your productivity index from this, you are calculating it to be 2 barrel per day per psi. What does these two indicates? These two indicates that when you are increasing your drawdown by 1 psi, you are going to get a gain of production 2 barrel per day. So based on this PI, you will be able to judge the drawdown as well as the flow rate. So from our reservoir, the fluid will flow only when there is a drawdown. That means at your flowing bottom hole pressure. So when you reduce your flowing bottom hole pressure below your reservoir pressure, you will see this will be your drawdown, del P. Only when there is a drawdown, you are going to get a production. And you get a production. If you further decrease your drawdown, you are going to get a higher production. And one thing you notice here is that you have this curve in the IPR below the bubble point pressure. This is the Vogel's behavior. In this region, you cannot use your productivity index. You have to use your Vogel's IPR. And when you reduce your reservoir pressure from the reservoir pressure and you reduce your flowing bottom hole pressure, when you reduce to 0, you are going to get the maximum production, which is Qmax. This is also called the AOF, the absolute open flow potential, which is basically when you are reducing your flowing bottom hole pressure to the atmospheric pressure at the perforation interval or the sand phase, you are going to get the highest production. Now let's move on to the outflow performance. In the outflow performance, you have two regions. You have this yellow region. This will be because of your hydrostatic pressure in your well. And the right side, this region will be because of your friction contribution. As you increase the flow rate, your friction will be increasing. Now let's see the blue one. This is the initial tubing curve. When the friction increases because of the high GOR, you are seeing an shifting of the tubing curve upwards. And when you are producing more water or your water cut is increasing, you are going to see a wall TPR curve shifting upwards. So this will depend on the factors such as the tubing size, the tubing head pressure, the water cut, the GLR, and the depth. So this, as we move further to the session, you are going to understand properly. When you are plotting inflow versus the outflow, like I said before in the nodal analysis, you will be noticing the intersection point. This is your, at this pressure, you will be producing at the flow rate when your node pressure or your PWF, flowing bottom hole pressure, is decreased. Similar to the curve C, as your flowing bottom hole pressure decreases, you have a higher production rate. But in the curve A, outflow performance curve A, you notice that your inflow performance curve is not intersecting with your outflow performance curve. Because of this, you are not going to get any production. Why? Because there is no continuity in your system. Only when there is an intersection, you are going to have a continuity, then only you will be producing some gas or liquid. Other than this, if you want your IPR curve to be improved from this to this, one thing you need to do is you need to stimulate your wellbore or the reservoir by hydraulic fracturing or your well stimulation techniques such as your matrix acid fracturing. For your IPR curve to move upwards, you are going to increase your flow from this rate to this rate. So that's exactly what happened when you, for example, hydraulic fracture your reservoir. You are going to see an increase in pressure, increase in the production. And this is the inflow versus the outflow curve. Now let's understand the multiphase flow in the vertical pipe. You have 4 possible flow regimes in the vertical pipe multiphase flow. You have the bubble flow, the slug flow, churn flow, and the annular flow. In the beginning, when your well is drilled and started producing, you may be producing with a single flow of only gas. But as you decrease your gas rate, as the gas rate decreases, you will be observing some liquid film around your wellbore and some droplets of liquid in the continuous medium of gas. So this is the annular flow. As you further decrease, as the gas rate further decreases, you will notice a non-continuous gas stream. In this case, your gas and your liquid will be flowing alternatively. And when the gas rate decreases farther down, your liquid is going to be continuous and you will be getting only bubbles of gas. Now let's see here, you have the superficial gas rate versus superficial liquid rate. As your superficial gas rate increases compared to your liquid rate, you have your annular flow. And if your superficial liquid rate is higher, you have bubble flow here because your superficial gas rate is very low. So that's what happened in the vertical tubing because of the multiphase flow. Now let's move on to the liquid loading. What exactly is a liquid loading? It is basically the inability of the produced gas to remove the produced liquids from the wellbore. When you have a new well with a high gas rate, you will be producing maybe only a single flow, the gas. As your gas production drops or your reservoir pressure decreases, you will because of some liquids producing, you will started noticing your single phase flow into a multi-phase flow. Like I just explained, in the multi-phase flow, your flow pattern will move from a slug flow to the bubble flow, and then finally you will be seeing only water in your well. In this case, you have zero gas production. Basically, your well is killed by water. Why? Because, like I said, only when there is a difference between your reservoir pressure and your flowing bottom hole pressure, you will see a production. But what happened here is, here you have the flowing bottom hole pressure. Flowing bottom hole pressure is basically your hydrostatic pressure, which is let's say rho g h. So what happened here? When you are producing only gas, your gas density is much lower compared to your fluid density. So because of higher density of liquid, you are going to have a higher flowing bottom hole pressure. So this will be higher. As this is higher, the differential pressure will be less. So you are going to see a decrease in the production because of an increase in the flowing bottom hole pressure. So as the rate decreases, you're going to have a lower production as your fluid flow from one pattern to the other flow pattern. You have a decrease in the gas rate, and eventually your well is full of liquid. So you need to take some measures to unload this liquid. Now let's understand first what is the loading mechanism. This mechanism is developed by Turner's, the liquid droplet transport model. Here he consider a liquid droplet. You have a liquid droplet here. In this liquid droplet, you have two forces that acting opposite. One is your drag force. Your drag force is basically your gas rate or your gas velocity, which will be trying to lift your gas or lift your liquid droplets. It will try to lift your liquid droplet. And the other force is your gravity. This will try to push your droplet downwards. Only when your velocity of gas is higher than your ability of your gravity to pull down the liquid droplets. If this is higher, only when this is higher, you are going to be able to lift this liquid to the surface. So he developed a formula for calculating this velocity of a gas velocity, critical gas velocity. If you have, if first you are going to know your liquid density, gas density, as well as your surface tension between the liquid and the gas inside your wellbore. Once you found your critical gas velocity, you will be able to calculate your critical gas rate. What is a critical gas rate? It is a minimum gas rate below which you will notice your fluid moving downwards. So it will accumulate to the wellbore. Because of that, you are going to see a increase in the flowing bottom hole pressure, and then basically it will reduce your gas production and kill your well. So for this calculation, this is the constant used by Turner. If your flowing bottom hole pressure is greater than 1000 psi, you are going to use your K value of 1.92, which is the Turner value. And for tubing head pressure less than your 1000 psi value, you will be using this value 1.59, the Coleman value. Now let's understand this liquid loading from your tubing performance curve. Like I said before, you have two regions, the hydrostatic part and the frictional part. And you have, this is the inflection point where your curve slope is 0. Now you are able to find your critical gas rate from this formula. Let's say this is your critical gas rate. Now let's assume one of your well is producing at this rate, at this flowing bottom hole pressure, is producing at this rate. So if this rate is above your critical gas rate, you are not going to see any liquid loading. So basically you are trying to produce gas from your well above the minimum flow rate or the critical gas rate. Now, if your well is producing below your critical gas rate, you are producing it at this BHP and at this rate. So when your flow rate is below your minimum flow rate, the critical gas rate, you are going to see a liquid loading problem, as well as you may produce some gas, but it will eventually load up with liquid. So you can predict this rate using the formula given here before. Now, like I explained before, when there is no intersection between your TPR and the IPR, there is no flow. So in this case, you may want to use artificial lift. And one thing is that you are going to use 10 feet per second of minimum gas velocity as a rule of thumb, and you will be able to calculate this critical gas rate very easily. Instead of, if you don't know the density of liquid and gas in your wellbore, you will just be using the velocity of gas rate as 10 feet per second. Now, how are we going to recognize some of the symptoms of liquid loading in gas well? The first thing is from your, from your decline curve analysis. In decline curve analysis, you are basically forecasting your production with time. This is your forecast production rate, but the actual production will be following this. There is a sharp drop in the production rate. So from this, you may be able to recognize that, okay, our well is liquid loaded. And the second thing is, when you are producing the liquids from the wellbore to the surface, it will flow through your orifice for pressure. In this case, you will be noticing some spikes in your tube and chart, your casing or your tubing, or because your well will be flowing liquid as well as gas. So there will be a difference in the pressure when it flows through the orifice. You will see a spike. And the third thing is, you will notice there is a increase in the casing pressure as well as the tubing pressure. The difference in casing and tubing pressure will increase. So if you plot this, your casing pressure will increase, your tubing pressure will decrease. So this may also be an indication of liquid loading problem. Now, let's understand the casing and the tubing in liquid loading condition. You have two fluids, water and gas, flowing from your reservoir to the wellbore. With time, you will see an increase in the water production. Let's say your tubing head pressure is 20 kg per centimeter square and your CHP is 50. This is 20 and you have your casing pressure of 50. And as you are producing as you produce more water, your tubing pressure is going to decrease because your tubing will be filled with liquid. So because of the hydrostatic pressure of the water that will act against your reservoir, and some of your gas will move towards casing annulus, and you will eventually see your tubing filled with liquid. So in this case, your tubing may decrease to 0 or your casing pressure may increase to 70 kg because instead of going your gas to the tubing, basically it will go to the casing side. So that's what happened, and you will be able to know from this difference in tubing and casing pressure, you will be able to know the liquid loading. Now there is an two identification method for liquid loading in gas well. One is the pressure gradient, which is either the flowing gradient survey or the static gradient survey. What you do in this gradient survey is you are lowering a memory gauge, the electronic memory gauge, through your tubing down to the wellbore. As you lower down your gauge, you are going to record the pressure, the gradient. So when there is a difference in gradient of gas versus liquid, there's a sharp difference in the gradient. So you may be able to you will be able to identify that this as your liquid level. So below this level in your tubing will be filled with liquid. So when you lower down your memory gauge, your EMG, you have to lower it up to the not up to the tubing shoe, above 5 to 10 feet above your 10 meter above your tubing shoe, because if you lower it below your tubing shoe, you are lowering this EMG using wire line. Your wire may be cut by the tubing shoe, so be careful when you are lowering. And the next is the production logging tool. From this PLT tool, you are also be able to identify the liquid loading. In production logging tool, we have 7 parameters. The gamma ray, which will be determining and will be used as a depth correlation. Casing color, which will also be used as a depth correlation. You have the turbine flow, which will determine the rate of the flow from the perforation interval or the producing zone. And then fluid temperature, you have the water holdup, and then the fluid density and the fluid pressure. One thing is you have the fluid capacitance and the fluid density. Fluid capacitance will measure the difference between the water and the hydrocarbons, and your fluid density will be measuring your water, hydrocarbon, liquid, and gas. From these two, you will be able to find out the water holdup. So this production logging tool will be able to identify whether you are producing a 2-phase or a 3-phase. flow in the production interval. Now, if you see here in your turbine flow meter, you notice that your gas rate decreases here in this region. That means that there are less gas coming out of your interval. And then you also notice your fluid temperature increasing and your water holdup. Water holdup is basically your liquid holdup, which is your fluid occupying the some interval of your tubing. So your water holdup also. So basically, you have more gas here, and at this interval, you have more water. So that you are also correlating with the fluid density, your fluid density increases. So you are identifying this as your water. And now we will be talking we're talking about the de-liquification technique. There are 4 categories in de-liquification technique. One is the surveillance, one is the mechanical and chemical and gas lift. In surveillance, we have 2 types. One is the cycling. In cycling, what you do is, first let's understand our wellhead, right? In wellhead, we have these valves, stack of valves. Like I said before, wellhead is a stack of valves. You have your bull plug, you have your bull plug flange, you have your swept valve or your crown valve. Actually, this picture shows the back side of the wellhead. You are going to see a wheel for these valves to open or close on the front side. You have your swept valve or the crown valve, you have your flow arm valve, and you have the upper master valve and the lower master valve. So what you do in the cycling is that you are going to, your well, first your gas is flowing through your tubing, right? This line to the GCS or your gas gathering station. And in cycling is that you want to shut your well. You are going to close this flow arm valve. When you close it, your hydrostatic column, some of the liquid column will drains back to the reservoir, which will be observed by increasing your wellhead pressure. If you put some pressure here, some pressure gauge here, this is your wellhead pressure, you are going to see an increase in the wellhead pressure. And it will charge your downhole, the well bore. And then when you open this flow arm valve, when you open it, a sudden pressure will be released from your casing, and it will push some of your liquids towards your tubing from the casing side to the tubing side. So you will be knocking out some water. Now let's see this. In the cycling, you close the well. When you close the well, suppose you have a liquid loading there. When you close the well, you are going to have a back pressure in this direction. So this back pressure will push the liquid back to the reservoir. So and also some gas will coming out of the reservoir. This will charge your casing annulus, and your pressure will increase in the casing. You will also notice some increase in the tubing. And when you open this valve, the flow arm valve, the tubing, there is a sudden pressure drop. So basically you are opening it to an atmospheric pressure. Or if you want your fluid, if you want to control your gas rate, you are going to put some bean also in your wellhead. So when you are opening the flow arm valve, there is a sudden pressure drop, and because of that, some of your gas will be pushing the liquid upwards. So it will push, and then you are going to be able to unload your liquid to the surface, right? And the second thing is the venting. This is also a surveillance method. Like I said, you have these wellhead valves, and in some wells, in some gas wells, you are going to be producing your gas with some of choke size or the bin sizes like 10 mm or 8 mm or 6 mm. And you have a bin housing like this. This is your bin housing. This is basically similar to your bull plug. Inside this, you are going to have a bin. So the fluid will flow through the bin. After bin, you are going to get your fluid to the flow arm, flow line, to the separator, or to the gas collection station, or the group gathering station. Okay, and you have this pressure. This will be your casing head pressure, and one pressure will be there, one pressure gauge. So this will be your after bin pressure, ABP. So in venting, what you do is that you are removing your bin. So you are producing it against the atmospheric pressure. So there is no back pressure. Now let's understand the venting. Like I said, you want to reduce your bottom hole pressure. Bottom hole pressure, increase in the bottom hole pressure due to the water. Basically, your bottom hole pressure is your hydrostatic pressure and your back pressure that will act against your reservoir. So in venting, you are decreasing your back pressure against the reservoir. So your bottom hole pressure will be reduced. And as you vent it, your well, you will see more gas coming out of your reservoir because you are reducing your bottom hole pressure. As more gas coming out, you will be able to lift your liquid to the surface. So this is very common practice for the liquid loading problem in ONGC. Usually some GCS or GGS personnel will go to the field and he will remove the bin from the bin housing, and he will be opening the well to the atmospheric pressure, reducing the bin pressure. So maybe you need to do this regularly also, depending on the fluid that is loaded in your wellbore. So first you need to identify your liquid level. At what level you have your liquid, up to what level in your wellbore you have the liquid. So first you need to know what is your liquid level. So based on that, you will be able to calculate how much time should I open my well, as well as in cycling also, how long should I shut in my well, as well as how long should I open. It will depend on your liquid level, which you may be able to find out using your gradient survey or your casing and pressure tubing, casing CHP and THP difference. One thing you can also use is that you may use echometer, which is the acoustic survey, usually which will be used in the artificially like sucker rod pumping. You will be shooting some acoustic waves down your annulus and the reflection you will getting. So based on the velocity of the sound waves, you are able to calculate the liquid level also. And the second technique is the mechanical type, which is the swap cup. This swap cup is basically like a bucket. You have like if you have a water well, you are, if the level is very deep, you are lowering your bucket with some wire, right? So similar to that, you are lowering your swap cup using the wire line tool. First, you need to determine the liquid level, and then you will, based on the liquid level and how much liquid you need to unload using the swap cup, you will also choose the wire line diameter, the wire diameter, because if you are exceeding the tensile strength of the wear line, you are going to lose your wear line, and the swap cup as well as the wear will drop into the sum. You are going to require some fishing job, which will cost more. And when you are doing the wear line, basically you are removing your bull plug, and then above the first you will close this crown valve, the swept valve. You will remove your bull plug, and then you will connect your lubricator, wear line lubricator above your crown valve. And wear line lubricator has a stripper as well as a BOP, and then you connect that with the reel in the wear line truck. And we have the chemical method, which is a surfactant type, or we call it the foam stick. Normally wells with gas liquid ratio of 1,000 to 10,000 cubic feet per barrel, you will be using this foam stick because you need a high GLR, because it will give some necessary agitation in order to make foam inside your wellbore. One lower limit is of 50% water cut, because if the water cut is less, it may be impossible for your surfactant to form some foaming. So what we do in the foaming, this is basically your foam stick. In foam stick also, you will open your bull plug, and then you will close your, you will open your bull plug, you close your swept valve or your master valve, and then you are going to drop this foam stick from here. After that, it will stay here, your foam stick will stay here, and then you will close your bull plug again, and then you are opening your swept valve, and then your foam stick is going to fall down to the tubing. And then you are going to shut your well. You wait for 30 minutes, 1 hour, depending upon the foaming rate, which you will be calculating before dropping, and also based on how much water is present inside the wellbore. So what the foam stick is doing to the reservoir is, our flowing bottom hole pressure is your hydrostatic pressure, right? And your hydrostatic pressure is, you can calculate it from rho GH. One thing you can do is you can modify this density of water. So the surfactant will be reducing the density of water due to foaming. So as the density decreases, your hydrostatic pressure will decrease, and you will be decreasing your flowing bottom hole pressure. So you are increasing your drawdown. So that's how you will be gaining your gas rate from the specific well where you are using your foam stick or the surfactant. Also, you can also do injection, liquid batch injection. You can inject from this line or this line, depending on your requirement. Continuous injection is also possible, but usually in ONGC, especially in Tripura asset, which is mainly the gas reservoir, we are producing gas only, we are using this foam stick, which is sometimes will be very effective for a specific well. You will gain around maybe 5,000 SCMD, standard cubic meter of gas per day, but other well, you will not see any gain in production of gas because of some reason will be you are not getting some of the liquid, some of the water in that well that much, as well as maybe because of the limiting GLR. And the next liquid unloading technique is you are going to size your production string. Like I said before, the TPR curve, in order to increase your velocity, your gas velocity, so that it will be above your critical gas rate, production rate. So you want your gas rate to be higher than your minimum flow rate. To do that, you are going to reduce your tubing ID. We call it the velocity string. Basically, we use the string as coil tubing, either 1.5 inch or 1/4 inch. We will be, instead of producing from the tubing, you are going to produce from the coil tubing, which you will hang to the wellhead. So what happened here is that as you decrease your tubing size, your IPR is shifting upwards. So you are producing, you may be producing less, but at this rate, because of the high drawdown, you may be producing more water. And you may produce less here. This will eventually result in water loading, and it may not be able to, at this pressure, it may not be able to unload some of the water by your flow rate. But once you reduce your tubing ID to the, let's say from 2 7/8 inches, which will have an internal diameter of 2.441 to 1.5 inches of the coil tubing, you are basically increasing the flow rate, the flow rate of gas inside your velocity string. So what you do is you are hanging your velocity string to the wellhead. You can either producing from your velocity string or from the annulus. Annulus means your tubing through 7/8 tubing and 1.5 inch velocity string. That is the coil tubing. So you can produce either from the annulus or the velocity string. But you are going, but here you are going to require modification in the wellhead. You are going to add one more valve to control this string, and you are going to require some packer for the tubing and casing annulus. The velocity string can be designed in the Prosper also. You can design it with your Excel also if you know the nodal analysis, the IPR and TPR. So this is two conditions. One condition is when you are producing from the, when you are producing your gas from the velocity string, which is 1.5 inches, which is run inside your, excuse me, I can see someone is writing something on the screen. Okay, in velocity string, you have the 1.5 inch tubing, 7/8 inch tubing, in which you will be writing, you will be lowering your 1.5 velocity string, inch velocity string, which is basically your coil tubing, and you are calculating based on the Turner or the Coleman, you are calculating the critical gas rate. So for this specific well, your flow rate is, your critical gas rate is 9,734 meter cube per day. And your predicted gas production is around 14,500 meter cube per day, which is higher than your critical gas rate when you are producing from the coil tubing. So as this is higher than your critical gas rate, you are not going to see a liquid loading inside your coil tubing. So it will be producing fluid at this rate, at this condition of the pressure. Now the case 2 is that when you are producing your fluid through the annulus of 27/8 and the annulus of 1.5 velocity string, the coil tubing. If you are producing your critical gas rate, calculated rate is around 20,000 meter cube per day, and your predicted rate is 14,084 meter cube per day, which is less than your predicted critical gas rate. So if you are producing from the annulus of 1.5 inch velocity string and the true 7/8 inch tubing, you are going to see liquid loading anyway. So if you compare these two, you are going to produce your gas using your velocity string, not from the annulus. Okay. Now